Happy Tuesday, and thank you for joining us for today's webinar entitled A Guide to Tool Setup and Strategies to Ensure Quality Output on Your DWX Mill. I am Dwight Blair, the Global Product Manager now of DGSHAPE Global, and I have here with me Greg Everett. He's from CR Dental Tool. He's the Business Development Manager. Greg, how's everything going today?
Very good.
Very good. You excited to be here at
Oh,
Roland?
yeah. Thanks a lot, Dwight. We appreciate the opportunity to be here, and hopefully we can share some good knowledge to everybody.
Awesome. That's actually what I'm planning on doing. So we're going to get right into what we're talking about today, and I know we have a lot of topics regarding tools, especially in today's industry. And the first thing we're going to discuss is tool characteristics, dimensions, and profiles. That's going to cover basically the dimensions of the tool so we can understand just what we're putting in our machine, the profiles that we're going to be set in CAM strategies, and how they are used when we're milling specific materials. The next thing is the rapid razor sharp torque hammer. And Greg, this is a new tool that came out, you guys released not too long ago, at least this year, right?
Oh yeah, we're excited about it.
Okay, and maybe one of the things that it does pretty good is PMMA material, right?
Yeah, PMMA, soft materials, denture, removables.
Got it. So
Absolutely.
later on, we're going to get back into that slide and kind of give you really the gamut of what that tool can do for you. Some of you guys might be on Facebook or LinkedIn and might have even seen a couple of videos that we've posted. The tool just really cuts through PMMA material quite quickly. The other thing we're going to talk about is expected yield. We get a lot of questions about how long these tools last and whatnot. Greg has actually done some very good research and tested all of the tools, especially the diamond tools, and he's going to discuss a story about a tool life or a tool story. And the other thing we're going to do is we're going to show you a live setup for setting tools up for production. And by that we mean taking the tools, making sure they're set properly in the milling burr positioner and put into the machine so we can get away from some of those fun support concerns we have down in the future. And then we're going to talk about CAM strategy, and this might be a foreign topic for some, but we're really talking about how the CAM software takes the tool dimensions and uses that for strategies, and we'll explain what those strategies are as best in brief detail as possible to avoid any confusion. And we're going to talk about the common tool challenges, some things like parting lines or poor surface quality issues that arise and how tools might influence that. And that will be the end. Greg, you ready to jump into this right now?
Yeah, let's do it.
All right. So the first thing we have is tool types. And Greg, there's one tool called a carbide. If you would like to explain what we would use this tool for, great materials for it.
Yeah, absolutely. I'll take that. In dental, we basically have two options. One is going to be your uncoated carbide tool, which is kind of a standard tool. And those are typically used in soft materials, wax, PMMA, etc., although they can be used in zirconia as well. And then the second type of tool that we see in dental is actually a diamond coated tool. And these are used primarily in zirconia, and it's essentially for longevity. The tools are actually coated in a real diamond that lets the tool last very much longer than a regular carbide tool.
Makes sense. Now, if I'm milling like a hard composite resin, now we can dry mill those. Would I use a diamond or a carbide tool for that?
You definitely want to go diamond for that. Those composites can be pretty hard on tools for sure.
Now, why would I want to use a carbide, for instance? I know we have users that say, hey, that's carbide, it's affordable, it should be able to mill it. Why would we not use a carbide?
Well, because of the characteristics of the material. If you use a tool that doesn't have a coating on it in that sort of material, the tool will work, but it's just going to wear out really fast.
Really fast.
In fact, I think you shared an experience with me recently where you were able to mill, 2 or 3 units before it
Yeah,
wore
it was
out,
more like the first portion of a roughing part of a bridge, and the tool just snapped right off real quickly, testing it out. So we want to make sure we're using the right tools for that. I know there's another class, hybrid tools, but really your main thing is going to be diamond and carbide. The basic difference, diamond is going to last you a lot longer than carbide, I'm sure.
Absolutely.
So the other thing when we talk about tool types is really the profile options. And the first thing we look at is a ball. We have 3 different profiles we're going to talk today. And Greg, if you can explain to us what you would use a ball tip tool for.
Yeah, so if you ever take a close look at your tooling, you'll notice that at the tip it has a profile. And the vast majority of the profiles that we use in the Roland device is actually ball. And those are used because the operations that we're doing during milling are 3D profiling. So the tool can be worked from several different angles. And then next, going into the next one that we have in the Roland device, that's actually a flat square-tipped profile, and those are used occasionally for surfaces that need to be flat. So like a screw seat or a hybrid abutment interface, that sort of application.
Now, if we wanted to do, let's say, a screw retained crown with a rounded tip, is that possible to still achieve?
It is possible. In fact, there are some strategies out there that do utilize the ball end mill for that. However, the optimal way to do it is with a flat.
Right, and the flat, you should have a couple of different sizes, just like you would have for the round, I'm assuming, right?
Exactly.
Now the third tool is also new, basically. It's a torque end tip, and some people like torque. What is that? Can you explain a little bit what the torque tool is and why we would use it?
Yeah, absolutely. So this is another profile that's really widely used on the industrial side. It's not so common in dental. However, we've recently brought it in for the roll-in device because it has a few benefits for roughing. We're able to, when used in a roughing tool, which is like your mass removal first tool, a torque profile tool will actually remove a lot more material per pass than, say, a ball tool.
Now, will we use the torque tool for instance for zirconia, or is it just for like waxes, PMMAs, and stuff like that?
Yeah. For the time being, you know, the tool that you mentioned, the new one is actually a torque profile tool. There are some talks in the background about doing it on the zirconia side as well.
Right.
But right now, yeah, it's just on those soft.
So let's expand on that a little bit. As far as doing it on the zirconia profile, I know the benefit is being able to dig into that material and cut it pretty quickly.
Absolutely.
If you still dig it in with a fast strategy, would that be ideal for zirconia, or should it be a little bit different?
There's some applications where we might want to utilize that sort of profile. And that might be large restorations like hybrids and, you know, big pucks where you really need to remove a lot of material quickly before you get to the restoration.
Gotcha. Now the next thing we're going to talk about is flute count, and I know we're talking about a lot of details about a specific tool, but these are very important to know. Yeah. So there's two flute types we're going to talk about today, and the first is the single flute design, and they're really for soft materials. But Greg, tell us a little bit more about single flutes and why we should use them.
Yeah, so essentially tool design is driven by the material characteristics. And when a tool's running, every time it turns, it takes a certain amount of material per revolution. Single flute tooling is advantageous because it lets us take a larger chip, a larger piece of material, at a given RPM. So at 20,000 RPM, I'm taking X chip because I'm doing one rotation at a time. And those are, like you said, the main application for that is in soft materials that might tend to gum up or heat up during the milling process.
Now, just for those novice users out there that might be getting their first milling device, explain what a chip is. I mean, we hear that, but what is that actually?
Yeah, I'll elaborate a little bit on that. So you can think of a chip as if you ever took a knife and tried to cut like some cheese or something and shave off a little bit of cheese, that's what a chip is. So on a very small scale, as the tool's rotating through the material, it's creating a little sliver of material. And the RPM and feed rate determine the size of that chip.
Gotcha. So that could be just like material waste, but it's basically chipping out of the material per revolution.
Yeah, it's the waste removed material.
Makes sense. Now, the second design we're going to talk about is a dual flute. This is for your medium to hard materials. Do you want to expand on that a little bit, Greg, and tell us what those are used for?
Absolutely. So you'll notice the vast majority of the tooling that's available out there is actually a two flute design, and those are used primarily in zirconia. It can be used in PMMA as long as the geometry is such that it works correctly. However, the main difference is that per revolution you actually get two cuts. So every time it turns around, it cuts twice. So inherently, at that same 20,000 RPM, you're actually getting double the amount of chips.
Gotcha. Now, I know one thing we didn't mention up here was the trio flute, or the flute with three-fluted tool. Why would you want to use a three-fluted tool, and is there any benefit over that than a two or a single?
So on the industrial side, if you're cutting aluminum or other harder alloys, adding flutes is is advantageous, if we're making metal parts. However, what you'll find out there is the vast majority of the tools are actually to flute because that just works better in dental materials.
Got it.
And it's really a function of getting the material out of the pocket.
Right.
And 3 flute tools just tend to clog. So.
And is that because that other third flute is not really hitting the material?
Yeah.
The other 2 are probably sweeping out more of the material waste?
Right. When you have a 3 flute tool, you're limited in the depth of the flute.
Gotcha.
Physically. Yeah, so it has to be more shallow.
That makes sense. All right. Well, another, should I say, characteristic of the tool is going to be chip channels. We just mentioned about chips, and now we talk about the chip channel. So tell us a little bit about the standard nano die and chip channels, what that means, what it is, and why it's important.
Yeah. So in the beginning of 2018, Sierra, we discovered that there was an issue or a potential issue with labs that are milling very large restorations. And what that is that when you're milling in a puck that's 18 millimeters or over, the tool can actually kind of start trapping that debris. And so what we did is we actually developed the second tool here, which should slide in. This is called the Tornado, and it has a new feature that's pretty apparent there. And that's called a chip channel.
Right.
And that feature actually encourages the material to move up and out in those applications, and it adds to the performance of the tool, the longevity of the tool, because we're not recutting that material.
Makes sense. Now, why is it important to channel out the material higher than where you're milling?
Excellent question. So as the material is being cut, it's creating debris, and that debris, if it's not moved out of the way, it'll actually be recut, and it'll contribute to the amount of abrasion on the tool. And in the worst case scenario, it can actually cause the tool to bind and cause damage to the restoration or the tool.
In that case, we're talking about heated up material that's in the pocket. That's why it's very important to use your air pressure to get all of that material waste out of the pocket, so it doesn't warm up and actually take away a margin or move into it, cause surface quality issues, I'm assuming, right?
A common thing that I see is actually, a suction unit that hasn't been, cleaned or maintained, or the air pressure is set incorrectly.
Right.
Those are very important things to keep in mind.
That makes sense. So the next thing we're going to talk about is design. So the first step up, we have a tool here. There's about 5 different characteristics of understanding just some specific geometries of the tool. Greg, if you would like to go through this and explain, first off, what a shank is.
Oh, yeah, absolutely. So I'll back up just a little bit. One of the most important things with tooling is that it needs to run very true. It can't wobble at all. Any amount of wobble is bad for the restoration, it's bad for the tool. And so one of the main contributors to the amount of tool wobble or run out is the design and manufacture of the actual shank. That shank has to be extremely concentric with the cutting edge of the tool. And so the tools that are manufactured by Sierra are held to a very, very high tolerance on the shank.
I can assume that if the shank is not fully or designed properly, or let's say it does wobble a little bit, that might even influence challenges with the collet or bend the collet in a sense.
Yeah, it can cause all kinds of trouble. So that's one of the benefits of a high quality tool.
Okay. Now the next thing we have is a taper, and I'll let you go ahead and take.
Yeah. So the taper is is essentially the blend from the cutting diameter, the size of the tool, all the way up to the shank. And so if you look at your tools, you'll notice that taper does change for the size of the tool. And then if we jump into the next one, the taper and the reach, which is measured from the tip to the beginning of the taper, are extremely important that it's represented correctly in the CAM software. What we see with a lot of labs that might be using an aftermarket tool is that this is not represented correctly, and we end up with material impacts and tool breakage because the CAM software doesn't know the shape. Doesn't know
it's a shape of the tool, right? And I know sometimes even with that, when we talk about the taper, it's also considered the neck. And if you don't have a long enough reach, that neck is going to rub up against the sides of the material walls, which will usually lead to tool slippage, or what we call that the tool slipping in the software. There is a chuck count, that's what we call it, and you will have a chuck error or something like that will pop on your machine. So want to make sure we have those dimensions properly. The next thing is the length of cut. Of course, that's the most important thing, but Greg, I'll let you discuss that.
So the length of cut is measured from the tip to the end of the cutting edge. And that's the theoretical maximum depth that the tool can operate at.
Okay.
Now, typically our lengths of cut are overkill. You know, we're right around 5 millimeters or so, depending on the tool. However, this tool that's actually illustrated is a 2 millimeter tool, and you usually won't see that digging down more than 1.5 millimeters per pass.
Okay, and why is it limited to 1.5? Should it be a little bit higher or lower than that? Can I go down 3 if I want to, or what?
You could, but it's actually a limitation of the material. You don't want to be too violent on the material as you're cutting. And so yeah, you could drive the tool that deep if the parameters are correct.
That makes sense. Makes sense. Last but not least, we have the cutting diameter, and I'll let you explain how that functions into the strategy, because I know we look at 2.0, and is that really the full width of the actual length?
Yeah,
okay.
Absolutely. So if you have a 2.0 millimeter tool, that measurement of the diameter of the tool is 2.0. That means that, and again, to elaborate on what you're saying, the CAM software must be accurate to that dimension, because, like, let's say your software says that it's 1.5, but you actually have a 2 millimeter tool in there. All your tool paths will be calculated on 1.5,
right,
and things will just be confused. And
a little confused because you got the wrong
window,
tool and the strategies are
Yeah.
different. Great point there. So that brings us to the new tool. So a lot of you guys are excited about this new tools. We've heard actually I know people have reached out to me directly, as well as our team, and you, of course. About the Rapid Razor Sharp 3.0 millimeter torque and burr. We want to discuss some of those benefits just to let our audience know what's going on. So the first one, I'll let you take this actually with the faster removable material.
Okay, so you'll notice by the picture that it's kind of a different looking tool. We already touched on the single flute benefits. It's a single flute torque profile tool, 3 millimeters in diameter. And the geometry is such that it's designed to remove material very fast.
Okay.
In fact, compared to the 2 millimeter ball, we can actually remove 6 to 8 times the amount of material per minute than that tool.
Now, is it because it's larger in diameter, or is it because of the design and it can actually cut into the material faster?
It's a recipe. It's all of the above. Yeah.
Got it. The next thing we have is minimizing cutting loads, and I'm assuming we're talking about the pressure that's on the tool, but you can explain that a little bit further.
Right. So that's always a concern, as we always want to minimize the amount of load that's on the tool, the machine, the profile, or the material. And so what we've done is all of the business end of this tool has a very high polish, so it's low friction, and the cutting edge is actually post-polished after the grind.
Gotcha.
So if you look at it under magnification, it's extremely sharp.
Makes sense. And then the third thing is optimized for larger materials. And I'm assuming we're talking about thickness, but let's go ahead.
The thickness of the puck. So, this thing's designed with removables in mind. And so a lot of the applications for removables, we're looking at like a 30 millimeter.
35, 40.
Maybe even up to a 40 sometimes.
Denture bases, partial bases, stuff like that.
We're much larger on this application.
Right.
So this tool actually has a 20 millimeter reach, so it can actually mill up to a 40 millimeter puck without any strategy modifications.
Understandable.
And so we're able to get into those deep areas with this.
And it's important that we mention that, because we talk about 20 millimeters as far as a reach is concerned. That's going to be half of whatever your material size is based on how the strategy cuts the material.
Exactly.
So if we go, let's say we have a 45 millimeter disc, yes, we can mill it, but the neck is going to be involved at that point because you're going past the actual full length of the tool.
Yeah. You can mill a larger puck, but you've got to have ample room around the part for the tool to fit.
Makes sense. The other thing is it prevents overheating, and explain how this tool does that.
So that actually comes back down to the chip size again. And because it's single flute, we're able to take a larger chip, which as the chip's evacuated out of the cut, it's able to take more heat with it because it's got more mass.
And go ahead.
And so in materials that tend to overheat and gum up, this tool eliminates that problem.
And gumming is going to cause challenges when you're milling and the material actually heats up enough where it grabs the tool at the bottom and prevents it. You get an error, or let's say you just start seeing a heated tip, which is a telltale sign that your strategies are probably too aggressive. You want to slow it down. The other thing is it's a unique shank design that reduces tool wear, and I know we touched on that earlier as far as making sure you have a quality shank, making sure it's precise, that keeps the wobble out and make sure we can go through it. We're going to, go through this next story. And basically, you actually took the time to sit down and you did a test on all of your diamond-coated tools as well as your other tools. And I know there's a lot of people out there, but I'll let you explain what you've done to get this data that we're going to look at today.
Yeah, absolutely. So, we get the question, hey, how long do the tools last in the roll-on device? And while it is definitely driven by the material that the lab's using, our diamond tools really offer a very good value to the lab. And so what we wanted to do was demonstrate that.
Got it. So your first step was building over 100,000 units, I believe, right?
Right, yeah, so many units.
Wow, wow.
Yeah, it actually took me a couple of weeks to finish. And so we milled 1,000 units, the same program over and over with a variety of different designs in it. And then we actually documented the results every 50 units, very detailed pictures of each puck, and microscope pictures of the tool so we can track the tool wear.
Makes sense. And then I know the other step was you quantified all that data, right? And you showed it in a way where we can actually see it today, even though it's a lot more to the story, but we're going to summarize it for you. So we'll go to the next step, and of course, we're going to look at the 1 millimeter tool wear over a certain period of time. So the first thing we have is 50 units, and I'll let you go ahead.
I'll run through that. So at 50 units, there's essentially zero wear. You're not going to see any sort of wear at all at that point. Now,
when we look for wear, what are we actually looking for at the tool? Like, is there a specific item? Is there like chipping, scratches? What are we looking for?
So I'm going to be going over that on the scope here in a minute, and I'll go into detail on how to look at that.
Sounds good. So at the 50 unit mark, we're looking at a pretty quality tool, pretty steam. Let's go to 500 units.
So at 500 units, we're actually starting to see a little bit of a wear facet, which is normal. That's what you're going to see during the life of the tool. And then at 1,000 units, now we're seeing some significant wear. And this tool is actually still cutting good. We weren't at the chip point at 1,000 units.
Gotcha.
And so in all honesty, it probably has another 100 units or so left.
Makes sense. I'm assuming, notice in the picture where it looks like more and more of the coating is going away as we continue to move forward. That's what's happening.
Yep, and that's what I mean by wear fast.
Gotcha.
Exactly.
All right, and the expected yield. So you milled the test, you did some studies, you've quantified that data, and now we have some statistics on the total time we can expect for the tool to be used, as well as units. I'll let you go ahead further.
Yeah, so one of the things that people might overlook a lot is the amount of runtime each tool actually experiences, and it's not equal.
No, it's not.
And so essentially, if you have a crown that says takes 20 minutes or so to mill, only about 5 minutes of that is going to be the roughing, the 2 millimeter tool. The next 13, 14 minutes is going to be the 1 millimeter. So it's a large percentage of the time.
Right, exactly.
And then the rest is going to be your detailing. And so what this little table illustrates is about the amount of units that we're going to see from each tool, and how far they can go and exactly how much it costs per unit per tool.
That makes sense. So for all of you out there that have been asking that question of how long these tools last and how much time and how much that cost is going to be, this is a great slide for you to take with you and screen cap on your computers, and definitely keep an eye out on it because it really does work. This is for the diamond coated tools, not the carbide, so just keep that in mind. Now that we've talked about tool dimensions and stuff, we're going to jump actually right into our other camera and talk about tool setup, because this is something we need to clarify. So I know this is basically simple. We have a milling burr positioner here, and then we also have our milling burr holder, and then we have tools. Sometimes the challenge is we usually rush and we set up our tools for our machine, and sometimes that can be inaccurate. So what I want to do is show you how to do this correctly. Even though this is in your user manual setup guide, you can definitely see how to do this, but it is important for you to see a correct way of doing it. So first thing I want to do is I want to take my milling burr positioner, and then I want to take my milling burr holder, and I want to place it inside. And I want the screw that we're going to drill in to face the front. So there should be a screw right there facing the front. Now the one part that we don't do properly is inserting the tool. So when we take and insert the tool, as you see here, I'm using the 3 millimeter. You might not be able to see the tip. We don't want to go top bottom. We actually want to go bottom top. And the reason why is we don't want the metal to chip anything on the tool. Now once we get this tool inside, as you see here, the one thing we're looking for is both the tips to be inside of the window. So if I turn this a little way where the camera can see it, we want the tip, this top of the shank to be inside of this top window, and we want the actual milling side to be inside of the window here, so it's in between. Once you have it in between, we can take our wrench and we can tighten up the screw. And once we do that, everything's been pretty much good to go, so we have a solid tool.
So let's jump into vPanel real quick and just discuss how we set up tools for production using the vPanel software. This is after we have set up the tool in the milling burr positioner, place it in a slot. As you notice, you see here on the vPanel home screen, we have 15 slots representative for all of the tooling slots in the automatic tool changer. And if you see these blue sections here, 1, 2, and 3 are highlighted with blue because that means we have a tool there that actually has tool life. As I hover over, you'll see like 99 hours. You can actually go up as many hours as you want. Triple digits is ideal. And I know for Sierra Dental Tool, the hours usually go from anywhere between 125 to 150 based on what your strategy should be. So I'm going to jump right here by easily accessing tooling setup. We're going to click on the milling burr management icon. And then when we get in here, as you notice, I have 3 tools set up already, but I haven't set up the 0.3 millimeter burr. I do name my tools by their product code. Some of you might name them by the size of the diameter of the cutting ability. Some of you might name them by the specific kind, like carbide, hybrid, diamond, or whatnot, or even a name like toric. But either way it goes, do you want to pick a naming convention that's easy for you to use? Now, if you notice here, when I click on this slide, all I need to do is go and select a tool. I only have 3 tools available to select, and I'm looking for the 0.3 millimeter burr to put in slot 4 to match the CAM software that I'm using. So I'm going to click cancel, and I need to register that tool first in order to do it. To do so, I'm going to click on the new burr, and then I'm going to click and add a name here, and my name is going to be the product code for that 0.3 millimeter burr as offered through Sierra Dental Tool, and I'm just going to give it a dummy replacement time of 99 hours. Now, these are carbide burrs. They're probably not going to last as long as hybrids, but just keep that in mind when you're going through this process. Your replacement time is important because if it's not there, you're not going to see any blue tracking of your tools. So you want to make sure that you have a replacement time set. Make sure you have the latest vPanel so you're not experiencing any bugs with setting replacement times properly. So if I go ahead and click Add Milling Burr, you'll notice that it added the burr with the proper replacement time here. If I am taking tools and placing them from one position to another, what I want to do is add a working time, or if there's another vPanel or another machine, or if there's a tool that I want to use as a backup and I want to replace that tool and put it in another slot and put a new tool in, I can do that by making sure I set the working time for the instant that's here. That's going to tie into Intelligent Tool Control. So I'm going to close this right now because I've already set up my tool, and then if I go back to this button here, I can now select my 0.3 millimeter burr and click OK, and notice it jumps right in here with its time for replacement. Now, when we talk about Intelligent Tool Control, there's a couple of things I want you to understand. I can select any slot here and set up a replacement tool. For instance, for my 1 millimeter, I'm going to go ahead and select my 1 millimeter tool, and now if you notice, I've selected the 1 millimeter tool, and I have a instance of 2 here, where initially I had an instance of 1, but it was just like these other tools. If I'm going to back up my 2 millimeter tool, I can select that here, and I can back up my 2 millimeter tool, and you'll notice the same thing happens. Your first instance is always going to be the first place that tool is found in the ATC from 1 to 15. Your second instance is going to be the next set that you select, and you actually set up that tool. Now, when it comes down to customized tool setups, we need to understand something here. You want to make sure that your tool setup in vPanel, as well as your manual tool positioning when you place a tool in the ATC or an automatic tool changer, matches what you see in Mailbox software or your CAM software. Most CAM softwares, when they're processed, they show you where the tools need to be in each slot, and you want to make sure you place your tools directly where the software is telling you to place them. And for those users that have the customized tool setup options in their CAM software, keep in mind, if you decide to place, let's say, your carbide tools on slots 1 through 4, and your PMMA tools, carbide tools on slots 6 through 9, and you have Intelligent Tool Control set up for 6 through 9, you're probably going to run into a data error. So make sure that your tools in Mailbox, or SimSys, or should I say CAM software, because we use Mailbox a lot here at Roland, but make sure your CAM software is matching your tool setup in vPanel as well as your manual positioning. vPanel and CAM software do not communicate with each other. vPanel just reads a process file from the CAM software and it tells it where to go. It does not know what tool you have in each specific slot unless you actually name it and match it accordingly. So let's just keep that in mind. Other than that, we'll jump right back into the PowerPoint. And sorry if I went too fast. Now we're going to talk about milling strategies just a bit, and I'm going to let Greg go over this real quick and discuss it with you. Greg, let's talk about the first two things. And we're going to be real basic with this. We're not going to get into too much detail, but we're going to talk about step overs and step downs to help you understand just how the machine moves and how strategies influence tool movement and material removal.
Right, yeah. So for those of us who might not know what a strategy is, it's basically the set of instructions that the CAM software follows for a particular type of job. So typically there'll be a strategy for crown, strategy for denture. There's a little difference between the type and the material. And so I'll just briefly go over a couple of the things that strategies control. This first set here on the screen is actually the amount of material that it's removing as the tool is going through the material. And the strategy will control the step over, which is the lateral horizontal material removal, and then the step down, which is your vertical material removal. And then on the next side here, these are what you call feeds and speeds. Very, very important. So on your XY feed rate, that's actually, you can think of that like a speed limit on a highway. It's setting a limit of how fast the tool can accelerate to in material. And that works in conjunction with the spindle speed, the RPM, revolutions per minute, to create that chip. And so if you change any of these parameters, the size of the chip changes.
And I mean, that's important. I know we talk about how fast we can drive the machine. It's always great to, let's say, get your machine going a little bit faster if we need to, but you really want to consider the material that you're milling. You also want to consider the tools that you're using, if they can handle the load, as well as the machine. The good thing about most of our CAM manufacturers today is they have software strategies that allow you to get the most life out of everything. We do have other users that are adjusting those strategies for their own specific uses, and that might either speed up or lessen the lifetime of a tool or a spindle or a collet. So these are things we want to keep in mind when we adjust strategies and just the basics, but this is a very good point to know of how they work. And now the next thing we're going to talk about is just the profiles, just to show you what that looks like. If we jump back into my computer real quick, usually when you get into processing a job, it's going to show you which tools should be in a specific spot. This is what this screen is for. So we have slot 1, slot 2, slot 3, and slot 16, which calls for the cleaning tool. You want to make sure your tools are matching this when the CAM software processes it. For this example, I'm using the pop-up and Millbox software. Of course, you might have other CAM softwares out there that you use, and they should have a profile like this to show you where your tool should be inside of the milling device. Now, the other thing I'm going to talk about is I'm going to let Greg talk about is the actual strategy and the setup and how that tool design influences the processing of the file. So go ahead.
Yeah, so earlier we were going on about the importance of the software knowing the shape of the tool. And so what you see here on Dwight's screen capture here is the physical measurements of the tool. And if this is mismatched to the tool that's in your device, it can just cause all kinds of different trouble points.
They might have a different brand for the rolling tool. These dimensions are not going to match up because the reach, as we were talking about earlier, would be different. The neck would be different. The shake might even be different, but you're still using CAM strategies that look for a different tooling profile, and then that starts to cause some of the issues that we see today, right?
Yeah, the match is critical.
Gotcha. Now, I know the next thing we're going to go to, if we go back to the PowerPoint, is just looking at a couple of different things on our new versus old tools, and I'll let you do that. So we're going to switch computers here, if you can hold on for a second, and we'll jump right into our computer view, and we'll show you just what a new tool looks like in an old tool. So Greg has it all set up. Let's get his computer up. There we go.
Yeah. So what we have here is a microscope view of a brand new diamond tool. And many labs have microscopes in labs, so this is actually a good way to evaluate the condition of your tools. And so a brand new tool, you're going to look at the cutting edge, which is this aspect, obviously, and what you're looking for in a new tool is that it's pristine. If there's any damage to it, then the tool life and yield will definitely suffer. Moving on, I'll go ahead and load a used tool in.
Might even be a good idea for users to have some type of microscope so they can really analyze tools and be sure they know if a tool is worn or not. What do you think about that?
Oh, I'm a huge fan of that. In fact, I'd love to see everybody have a cheap digital microscope so we can email pictures back and forth. So here we go. Here's our used tool, and so this is actually the exact same tool. On this one is actually if you see the silver aspect on the cutting edge, that's what we call a wear facet, and as the tool operates during its lifetime, eventually it's going to wear through the diamond and get into the underlaying carbide. Now this tool actually has a lot of life left in it, but what I like to do is tell people that what you should do is keep an eye on this this wear pattern as your tools progress, and eventually it'll get to a point to where it'll be too dull to cut, and then that's when it's time to change the tool.
Troubleshooting. Just wanted to touch a couple of bases on some of the things we've heard come up from a few users, and that first concept becomes this lovely picture that we see here called parting lines around the restoration. You can also call this equator lines depending on who you are. But what would be some things that a parting line issue may relate to as tooling issue?
Yeah. So parting lines, the caveat here is that they can actually be caused by a number of different things. But if it is driven by the tool, it's most likely caused by a run out issue. And so that's either a worn tool that's worn unevenly because maybe a collet wasn't maintained correctly, or something along those lines. So usually if you're looking at this, let's take a look at the tool under the microscope. If the tool's good, then we got to look at calibration and all the other normal troubleshooting stuff.
That makes sense. Now, I know we talk about parting line issues. There's a lot of other things that could definitely influence parting line issues. Tooling could be one of them. It could be software. It could be calibration. It could be a few other things. But we basically want to make sure we rule out things before we assume that it's one or the other, right? Now, the other thing we have is our lovely chipping issue, and I really haven't seen this come about. I know that Roland has been making some very good machines, and the quality has been getting better. We don't see chipping unless somebody's not taking care of their tools, probably. But what would be some of the things that the tool could influence a chipping issue?
So at a certain point in the tool's lifespan, it will become dull to a point to where it doesn't cut efficiently. And again, you can go back to the cheese example I used earlier. Try to cut the cheese with the handle of a knife. It's just not going to work as well. And so typically people intuitively think that the 1mm tool is causing chipping. However, it actually is possible that the 2mm roughing tool causes chipping too. If it's worn to a place to where as it's cutting, it's actually traumatizing and cracking the zirconia at a microscopic level, it can also create margin chipping. And so definitely just keep an eye on the condition of the tools as you're running.
Got it. And then the other thing that is not always live, but sometimes it can pop up, and I know this happened to me when I first used was this large ridges, and I actually milled a bridge, and I was like, man, this bridge looks great. And then I milled another one. I said, wow, that first bridge I did looks quite terrible. What could lead to large ridges on the occlusal surface or some insufficient surface quality concerns?
Yeah, so this is actually a really good callback to your tool setup demo here. And what can cause this sort of issue, and it can happen in zirconia or whatever you're milling, this essentially is a tool in the wrong slot. And so those large areas where it was taken out of the interproximal, the machine was expecting a 0.6, but it actually had a 2.
Now, I know this can also happen for wet mill users. You have a wet mill, a DWX 42W or 4W, and sometimes if you put the wrong tool in the wrong spot, it can't calculate for that. So if you have a 1mm tool, it's going to expect that you have a 2.5, and that might break a tool. These are definitely the things that you want to be concerned about. So as we come to the closing thoughts of our webinar, we want to promote this idea of validation and a happy marriage. Your CAM software and your tools as well as your materials and your milling device all must marry each other with strategies as well as setup. And the setup and strategies need to be conformed to the materials that you're milling. And if all those things are married, then you should have much success using our milling devices. And if you have questions about that, you can always reach out to your reseller. Other than that, let's talk about a couple of frequently asked questions, if you don't mind. And if you do have any questions, you can definitely send them at this time, and we will definitely type them in, and we'll definitely try to answer those afterwards. But here are some that we normally hear about from some of our users that come up to us at trade shows or over the phone. And basically, the first question is, will the Rapid Razor Sharp 3.0 millimeter toric burr be available for the removable denture kit?
So yeah, that's actually something that's being worked on behind the scenes, and we expect that to be released with the next software update.
And that could be for Mailbox users. I know for sure that's coming out. If you have another CAM software besides SimSystems Mailbox, you do want to reach out to your reseller and try to see if that's something that they're going to have available for you, because our kit is open and every user should be able to use it. The next question I'm going to talk about is, where can a user purchase Sierra Dental Tool?
Right, yeah. So my recommendation on that is to reach out again to your reseller and ask that question. And if you need a specific answer to that, my email will be available at the end of this webinar.
Sounds great. And last but not least, we also have another question. The tool life doesn't record in vPanel, and when you fix it, it stops recording. What should you do next? That is a very good question. I just want to put this question here as we are working on that issue. We know that when you reinstall vPanel, it usually does work, so you can always try that. You might also have to reinstall the driver, but if it still pops out, just know that we're working on it, and once we have a full fix, we'll get that back to you. And now we'll open it up to all questions that might be there, and it looks like we're out of time right now. But if you do have questions that you're sending right now, we'll answer them later via email. And we thank you for your time today, because yes, we are at that point. And once again, if you have any questions, you can always contact us. My name is Dwight. This is Greg. We're both on social media a lot, and we have email addresses there for you to communicate with us. And Greg,
yeah, thanks a lot, Dwight. Sierra really appreciates the opportunity to sit down with you guys today, and look forward to supporting the industry.
Likewise. Thank you once again for your time and joining us, and have a great day. Happy milling.